From the very beginning, the universe was a tempest. Not the roaring storms of Earth, but a turbulence on a scale that dwarfs comprehension as seething. Churning expanse of energy, matter, and light in its most primordial form. The first whispers of existence were not orderly galaxies or spiraling stars, but quantum fluctuations minute, ephemeral disturbances in the fabric of space-time itself. Out of this chaos, something extraordinary emerged. Patterns began to crystallize. Particles aligned. Gas coalesced. Gravity stitched the first structures into the cosmic tapestry. What was once random became coherent. What was once chaotic became structured. This is the story of how the cosmos learned to organize itself, how the seeds of order were sown amid turbulence, and how from quantum uncertainty, the grand architecture of the universe arose. Today, as we look out into the universe, we see the result of that primordial choreography, the vast cosmic web, intricate galaxy clusters, and ultimately, our own ordered planet, teeming with life. But beneath this apparent harmony lies the ever-present question: why does chaos, so inherently destructive and unpredictable, so reliably produce order? In this documentary, we explore the origins of cosmic order, tracing the journey from random quantum fluctuations to the structured elegance of the universe we inhabit. We will examine the forces, events, and principles that shape the cosmos, probe the lingering mysteries at the frontier of physics, and reflect on how this story mirrors the order we see on Earth and in our own lives. So, how did a universe born from chaos find its form? The answer begins with a concept known as inflation. In the first fraction of a second after the Big Bang, the universe expanded at an unimaginable rate, stretching those tiny quantum fluctuations to cosmic scales. Think of it like this. You take a tiny, crinkled piece of foil and instantly stretch it out to the size of a continent. Every little bump and wrinkle on that foil is now a vast mountain range or a deep valley. These wrinkles in space-time became the seeds of cosmic structure. Areas that were slightly denser than average began to pull in more matter due to gravity, while less dense regions became the great voids we see between galaxies. It was the first act of cosmic sculpting, turning pure randomness into a blueprint for the future. But gravity couldn't do it all alone. As the universe cooled, fundamental forces like electromagnetism came into play. Protons and electrons, once flying free in a hot plasma, combined to form neutral atoms. This event, known as recombination, made the universe transparent for the first time. Light could finally travel freely, and what we now see as the cosmic microwave background radiation is a snapshot of this pivotal moment, a baby picture of the universe just 380,000 years old. This ancient light reveals the very same density fluctuations that inflation had magnified, confirming that the seeds of today's galaxies were planted in the universe's first moments. These tiny temperature variations, just 1 part in 100,000, were the gravitational wells where matter would begin to accumulate over billions of years. Over eons, gravity continued its patient work. The slightly denser regions grew, pulling in gas and dark matter to form vast, interconnected filaments. This is the cosmic web, the largest known structure in the universe. At the intersections of these filaments, where matter was most concentrated, gravity's pull was strongest. Here, gas clouds collapsed under their own weight, igniting the first stars and forming the first proto-galaxies. It's a process of runaway growth. The more massive an object becomes, the more gravity it exerts, and the more material it attracts. This gravitational snowball effect is how we get from a nearly uniform soup of matter to the stunningly complex galaxies, stars, and planets we see today. The chaos wasn't erased. This brings us to a profound principle. Order doesn't just arise in spite of chaos. It often arises because of it. From the formation of snowflakes to the spiraling arms of a galaxy, complex systems often find stable, ordered states when they are far from equilibrium. The universe is the ultimate example of this. It's a dynamic, evolving system, constantly balancing the organizing force of gravity against the disruptive energy of stars and supernovas. The very turbulence that once defined the early cosmos is now contained within galaxies, fueling star formation and driving cosmic evolution. The universe isn't a static crystal. It's a living, breathing system where chaos and order are locked in an eternal, creative dance. The story of cosmic order is our own origin story. The atoms in our bodies were forged in the hearts of stars that formed within these cosmic structures, all tracing back to those initial quantum fluctuations. It's a humbling reminder that we are intrinsically connected to the grandest story of all, the story of a universe that found its way from chaos to consciousness. There are still many mysteries to solve, like the nature of dark matter and dark energy, which play crucial roles in this cosmic architecture. But as we continue to explore, we get closer to understanding not just how the universe works, but our own place within it. To understand how order emerged from chaos, we must journey back to the very beginning, to the foundation of reality itself, the quantum world. Picture this: the first fractions of a second after the Big Bang. The universe isn't what we know today. It's an almost incomprehensibly hot, dense, and uniform soup of energy. There are no stars, no galaxies, not even atoms. This primordial plasma is a chaotic dance of radiation and elementary particles, all zipping around at nearly the speed of light, colliding and interacting in what looks like absolute disorder. But even in this apparent randomness, the universe wasn't perfectly uniform. This is where quantum mechanics comes in. It's the rulebook for the microscopic world, and it tells us that uncertainty is built into the fabric of reality. On the tiniest scales, particles and energy fields are constantly fluctuating, popping in and out of existence. Physicists call these quantum fluctuations. Think of it this way: even the vacuum of space is never truly empty. It's a fizzing, bubbling sea of energy where tiny, random variations are happening everywhere, all the time. Normally, they're fleeting and cancel each other out. But during a period known as cosmic inflation, something incredible happened. In a fraction of a second, the universe expanded exponentially. This cataclysmic expansion took those microscopic quantum ripples and stretched them across the cosmos. In an instant, tiny perturbations became macroscopic, imprinted on scales that would one day span billions of light years. And here we find a beautiful paradox. The chaos of random quantum fluctuations became the very seed of cosmic order. Without these tiny irregularities, gravity would have had nothing to grab onto, and the universe might have remained a featureless, empty void forever. As the universe continued to expand, it also cooled. About 380,000 years after the Big Bang, a crucial event occurred, a moment known as recombination. The universe cooled enough for electrons to combine with protons, forming the first neutral hydrogen atoms. Before this, photons, particles of light, were trapped in the dense plasma, bouncing around like pinballs. Now, they were free to stream across the cosmos for the first time. This ancient light is still traveling today, and we can detect it. It's called the cosmic microwave background, or CMB. The CMB is a faint thermal echo of the early universe, a snapshot of that primordial chaos and its newborn patterns. It's like a cosmic Rosetta Stone, and when we look at it, we see that the early universe wasn't perfectly smooth. There were tiny differences in temperature and density, about 1 part in 100,000. These minuscule differences were everything. The slightly denser regions had a slightly stronger gravitational pull. So over millions and then billions of years, these overdense patches acted like cosmic seeds, pulling in more and more surrounding matter. This is the heart of structure formation, order emerging from the initial irregularities written into the fabric of space itself. Gravity, the universe's great organizer, took charge. Where there was a little more mass, even more mass accumulated. Where there was slightly less, vast empty spaces, which we call voids, expanded. Over cosmic time, this gravitational snowball effect sculpted the universe into the grand structure we see today, the cosmic web. It's a breathtaking, interconnected network of filaments, nodes, and voids, spanning billions of light years. Galaxies and galaxy clusters aren't scattered randomly. They trace these glowing filaments, forming a magnificent pattern rooted in the quantum randomness of the universe's first moments. But quantum fluctuations and gravity aren't the whole story. There's another fundamental principle at play: entropy. You've probably heard of it as a measure of disorder. The second law of thermodynamics states that the total entropy of a closed system always tends to increase. The universe as a whole is becoming more disordered. So how do we get complex structures like galaxies, stars, and planets? Here's the fascinating part. While the overall entropy of the cosmos grows, pockets of low entropy, highly ordered structures can form locally. Think of a refrigerator. It creates a cold, ordered space inside, but it does so by pumping out heat and creating more disorder in the room around it. The universe does something similar. As it expands and cools, gravity pulls matter together, creating localized islands of incredible order. Like our solar system and life on Earth, even as the universe as a whole moves towards a state of maximum entropy. This delicate dance between chaos and structure, between randomness and physical law, is the foundation of everything. The universe is a system balanced on a knife's edge between disorder and order, where the seeds of complexity sprout naturally from the fundamental rules of physics. The echoes of this cosmic ordering resonate all around us, right here on Earth. Look at the branching patterns of a river delta, the fractal geometry of a fern or a snowflake, or the self-organizing dynamics of a weather system. These are all reflections of the same principles of emergent order that first appeared at the cosmic scale. What began as imperceptible quantum ripples billions of years ago cascaded through time and space to create the intricate beauty of the world we know, and ultimately, life itself. We've traced the incredible journey from the chaotic quantum foam of the infant universe to the vast, orderly scaffolding of the cosmic web. It's a story of how, against all odds, structure arises from randomness. Last time, we peeked into the universe's infancy, discovering the invisible quantum jitters that shaped its destiny. Today, we're going to see what those jitters grew up to be, the magnificent, tangible structures that define our cosmos. From the sprawling filaments of the cosmic web to the glittering cities of galaxy clusters, the universe reveals a stunning, almost geometric order, a pattern that emerged from primordial chaos over billions of years. The most breathtaking example of this order is the cosmic web, a vast, interconnected network of filaments, nodes and voids stretching across the entire observable universe. Think of it as a three-dimensional spiderweb, but on a scale that boggles the mind. The threads of this web are made of dark matter, gas, and countless galaxies. And they aren't random. They are the direct descendants of those early quantum fluctuations, stretched and amplified by gravity and cosmic expansion over eons. Imagine tracing one of these filaments. It starts as a tiny ripple in the fabric of space-time, and as gravity pulls matter in, it grows into a colossal bridge connecting clusters of galaxies. The galaxies themselves tend to gather at the intersections of these filaments, like bustling hubs in a cosmic superhighway. But the empty spaces between them, the voids, are just as crucial. These vast expanses of near-nothingness provide the contrast that makes the structure stand out. Without these voids, matter would have collapsed more evenly, and the grand web-like pattern we see today would have never formed. Discovering this web was a game-changer. It wasn't until the late 20th century, with massive projects like the Sloan Digital Sky Survey, that we started mapping millions of galaxies and saw the big picture. What once looked like isolated islands of stars was suddenly revealed to be part of a single, interconnected system spanning hundreds of millions of light years. It completely transformed our understanding of the universe's architecture. Now, let's zoom in on the nodes of this web, the galaxy clusters. These are the most massive, gravitationally bound objects in the universe. Cosmic megacities containing hundreds or even thousands of galaxies, and they are far from static. Inside these clusters, it's a constant dance of chaos and order. Galaxies collide and merge. Intergalactic gas is superheated to tens of millions of degrees. And all of it is held together by the invisible gravitational scaffolding of dark matter. Galaxy clusters are incredible cosmic laboratories. When two of them collide, it's a spectacular event that teaches us so much. Take the famous bullet cluster, for example. Here, two clusters smashed into each other at millions of kilometers per hour. The hot gas from each cluster collided and slowed down, but the galaxies and, most importantly, the dark matter passed right through each other. This separation gave us one of the most direct and powerful pieces of evidence for the existence of dark matter. Because clusters form in the densest regions of the cosmic web, their locations act like glowing markers on a map, tracing the underlying gravitational structure of the universe. By studying them, astronomers can essentially rewind the clock, connecting the grand order we see today all the way back to those tiny quantum ripples at the very beginning of time. But the scale of order doesn't stop there. Beyond clusters, we find superclusters, the largest known structures in the cosmos. These are truly gargantuan collections of galaxy clusters, capable of spanning over 500 million light-years. Our own cosmic neighborhood is part of one, the Laniakea supercluster, discovered in 2014. Laniakea contains tens of thousands of galaxies, including our Milky Way, all flowing along shared gravitational pathways toward a central point called the Great Attractor. It's a breathtaking vision of cosmic unity, all of us surfing the same gravitational wave. And of course, we have to talk about the voids again. These regions of near-total emptiness can stretch over 300 million light-years across. They are not just passive gaps, they actively shape the cosmic landscape. Their emptiness allows gravity to more effectively channel matter along the filaments, sharpening the contrast between the dense clusters and the empty space. In the cosmos, order is sculpted just as much by what isn't there as by what is. Underpinning all of this visible structure is a mysterious substance we call dark matter. It doesn't emit or absorb light, but its gravitational pull is the glue that holds everything together. Dark matter forms the invisible scaffolding upon which the entire cosmic web is built. Without it, gravity wouldn't be strong enough to form these structures. Galaxies would be scattered randomly, and the universe would be a chaotic mess. Then there's its equally enigmatic counterpart, dark energy. This is the mysterious force that's causing the expansion of the universe to accelerate. So, we have this incredible cosmic balancing act. Dark matter works to pull things together and build structure, while dark energy works to push everything apart. The delicate interplay between these two forces is what allowed the universe's intricate order to emerge at just the right pace. Our understanding of all this isn't just based on theory. It's built on decades of groundbreaking observations. It began with the cosmic microwave background, the universe's baby picture, which first showed us the tiny seeds of structure. Then came the large-scale galaxy surveys that mapped the cosmic web in stunning detail. We use gravitational lensing, the way light bends around massive objects, to see the invisible dark matter scaffolding. And we use powerful computer simulations, like the Millennium and Illustris projects, to model billions of years of cosmic evolution, turning abstract physics into a visual masterpiece that beautifully matches what our telescopes see. All of this confirms a profound truth. The order we see in the universe isn't a fluke. It's real, it's measurable, and it's fundamentally linked to the chaotic quantum processes that took place in the first moments of existence. What's truly amazing is how this predictable order emerges from a foundation of chaos. The filaments, clusters, and superclusters all form according to precise physical laws, like gravity and thermodynamics. Yet these laws operate on the random, unpredictable nature of quantum fluctuations. This is what we call an emergent phenomenon. Order arises naturally from a system that is fundamentally chaotic at its smallest scales. It's a pattern we see everywhere in nature, in the branching of rivers, the jagged forks of lightning, the intricate veins of a leaf. The universe itself is the ultimate demonstration that chaos isn't the opposite of order. It's the raw material from which order is built. Have you ever looked up at the stars and wondered how all of this came to be? From the wild, random chaos of the Big Bang, how did the universe sculpt such breathtaking order? We see galaxies, stars, planets, one of the biggest paradoxes in all of science. We have a pretty good handle on the universe's large-scale structure, but the deep question remains: why does chaos so consistently give birth to order? Random fluctuations, violent collisions, cosmic turbulence, these all sound incredibly destructive. Yet over billions of years, these very forces have conspired to build the intricate cosmic web we see today. The exact mechanisms that allow this emergent order to arise are still a frontier of scientific inquiry. In physics, we have a concept for this: emergence. It describes how complex, organized systems arise from simple, often chaotic interactions. Think of a snowflake. It's intricate. Six-sided symmetry isn't programmed into a single water molecule. It emerges from simple rules of attraction as water freezes. We see it in ant colonies, where individual ants following basic commands create a superorganism, and in hurricanes, where atmospheric chaos organizes into a swirling vortex. On a cosmic scale, the same principle is at play. Tiny, random quantum fluctuations in the baby universe were stretched to enormous sizes during cosmic inflation. Then, gravity took over, pulling matter together, sculpting these fluctuations into the vast filaments and clusters of galaxies that span the cosmos. You can see the parallels. The branching patterns of a river delta echo the galactic filaments. The swirl of a seashell mirrors a spiral galaxy. But this just leads to a deeper question. Why is the universe so good at this? Why does matter, left to its own devices, spontaneously organize itself into these beautiful, coherent patterns instead of just dissipating into a bland, uniform soup? Some physicists believe the answer lies in the fundamental symmetries of nature. Laws. The laws of physics aren't just a random collection of rules. They are bound by deep principles like the conservation of energy and momentum. These underlying symmetries act like channels, guiding the flow of chaos and making the emergence of structure not just possible, but perhaps even inevitable. When we talk about cosmic architecture, we have to talk about gravity. It's the master builder of the universe. Unlike other forces, gravity is always attractive, and it works over immense distances. It's relentless. In the early universe, even the tiniest regions that were slightly denser than their surroundings started to pull in more and more matter. Over billions of years, this gravitational snowball effect amplified those small differences, pulling matter into the long, delicate filaments and dense clusters of the cosmic web, leaving behind vast, empty voids. Without gravity's steady, organizing hand, those initial random fluctuations would have remained just that random and fleeting. But gravity isn't the whole story. You also have to consider entropy, the measure of disorder. You've probably heard of the second law of thermodynamics, which states that the total entropy or disorder in a closed system always increases. The universe as a whole is becoming more chaotic. So how does order arise? The key is that while the total entropy goes up, localized pockets of decreasing entropy can and do form. Star is a perfect example. It's an incredibly ordered, stable system that forms from a chaotic cloud of gas and dust. Our planet and life itself are stunning examples of localized order. So, chaos doesn't oppose order, creates the raw material and the energetic landscape upon which order can build itself, all while the universe's overall disorder continues to rise. This creates a beautiful cosmic tension, a dynamic dance between order and chaos that we can see happening right now. Look at images from the Hubble telescope of vast nebulas, the stellar nurseries of our galaxy. You can see turbulent clouds of gas collapsing under their own gravity to form new stars. But it's not a smooth process. Intense magnetic fields, blistering radiation from young stars, and violent shock waves from supernova explosions push back, injecting fresh turbulence into the clouds. This chaos prevents everything from just collapsing into one giant blob. The result is structured complexity. The chaotic forces don't destroy the order. They sculpt it, creating intricate details and influencing where and how stars form. This principal order, emerging through a constant negotiation with chaos, is a theme that repeats itself across all of nature. From the grandest cosmic scales right down to the processes that shape our own world. But even with this framework, we're left with some profound, unanswered questions that push the very limits of our understanding. Take dark matter. You know it provides the invisible scaffolding upon which galaxies are built. It's the gravitational backbone of the cosmos. But we have no idea what it actually is. Could its unknown properties be playing a hidden role in how chaos is channeled into structure? What if dark matter interacts with itself in ways we haven't predicted, creating new pathways for organization? Then there's dark energy, the mysterious force that's causing the expansion of the universe to accelerate. It's essentially pushing everything apart. How does this cosmic push affect the pull of gravity? Is it making it harder for new structures to form? What's its ultimate endgame? Could dark energy eventually become so dominant that it tears apart the very galaxies, stars, and planets that gravity so painstakingly assembled, returning the universe to a state of cold, empty chaos? We also have to grapple with the initial conditions of the universe itself. Why did those quantum fluctuations exist in the first place? And why did they have the exact right strength, not too strong, not too weak to seed the structures we see today? If they were just a tiny bit different, we could have ended up in a universe that was either a chaotic and density mess or a smooth, featureless void with no galaxies at all. And this leads to the puzzle of the arrow of time. Entropy gives time its direction, yet life and stars represent a local reversal of that arrow. Why is our universe so perfectly balanced to allow for these pockets of order to emerge and persist for billions of years? To really appreciate this cosmic balancing act, we can turn to chaos theory. This is a field of mathematics that helps us understand systems that are highly sensitive and unpredictable. You might have heard of the butterfly effect. The idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. This is what mathematicians call sensitive dependence on initial conditions. Tiny, almost immeasurable differences at the start can lead to wildly different outcomes later on. In cosmology, this means those minuscule quantum fluctuations in the early universe were the cosmic butterflies. A slightly different pattern of ripples could have resulted in a completely different cosmos. The fact that our universe produced such a rich tapestry of filaments, clusters, and voids is astonishing. It suggests one of two things. Either the initial conditions of our universe were exquisitely fine-tuned, almost as if by design. The emergence of order is a much more robust and inevitable consequence of the laws of physics than we currently understand. This has led scientists to explore some truly mind-bending ideas at the speculative edge of physics. One is the multiverse. Perhaps our universe is just one of many, each with slightly different physical laws or initial conditions. In this vast cosmic lottery, most universes might be sterile and chaotic. We just happen to find ourselves in one of the lucky ones, where the balance between chaos and order was just right for stars, planets, and observers like us to exist. Another idea is the concept of a self-organizing universe. Some models propose that the laws of physics themselves might not be static. Perhaps they evolve over time, naturally favoring configurations that lead to more complexity and order. It's a form of cosmic natural selection, where the universe learns to create structure. When some researchers are approaching this from a completely different angle, information theory, they ask, what if the universe is fundamentally a giant information processing system? In this view, the emergence of order isn't just about matter and energy, but about the creation of complex patterns of information. Structure arises naturally, just as it does in a computer simulation running on fundamental quantum rules. These mysteries of cosmic order aren't just abstract puzzles for physicists. They connect directly to the most fundamental questions of our own existence. Why are we here? Why do we find ourselves in a universe that is not just habitable, but comprehensible? Are we the result of a lucky cosmic accident? Or are we the natural, perhaps even inevitable, product of physical laws that favor the emergence of complexity in life? The patterns forged in cosmic fire didn't stop at galaxies and stars. The story of the universe, the tale of chaos birthing order, isn't just a distant fable written in the stars or a concept trapped in abstract simulations. It's a story that reaches all the way down to our own planet, into the very fabric of life, and even into the technologies we build every day. Earth itself is a breathtaking product of this cosmic structural world forged from the outcomes of billions of years of emergent order. Every single atom in our bodies, every grain of sand on our beaches, has its origins in stars and galaxies, all shaped by this incredible dance between randomness and order. The hydrogen, helium, and trace elements that seeded the early universe gathered along invisible filaments of dark matter. In regions of higher density, stars ignited, fusing those light elements into heavier ones. Eventually, massive stars exploded as supernova, scattering these newly forged elements across the cosmos, seeding new generations of stars and planets. Our own solar system is a masterpiece of this cosmic choreography. The Earth itself coalesced from a swirling protoplanetary disk, a chaotic mix of dust and gas shaped by gravitational forces, turbulence, and endless collisions. These chaotic processes, playing out over millions of years, miraculously produced a stable orbit, liquid water, and the perfect conditions for life to begin. Without this delicate balance between a chaotic formation and the steady hand of gravitational order, our planet might never have become the habitable world we call home. Life, when you get right down to it, is structured chaos. Biological systems are masters at harnessing randomness to create intricate order. Think about genetic mutations. They're inherently random, yet they provide the crucial variation that natural selection needs to work its magic. Evolution, in essence, is a cosmic extension of the very same principle we see in galaxy formation. From tiny, unpredictable fluctuations, magnificent and complex structures emerge. The patterns of life beautifully mirror those we see in the cosmos. The branching of trees, the networks of rivers, the circuits in our brains, and even our own vascular systems all echo the principles of emergent structure. Strikingly similar to the cosmic web, nature shows us, again and again, that chaos, when constrained by physical laws, becomes the raw material for breathtaking organization. Earth's own systems, its weather, climate, and geology, are further proof of structured chaos in action. The turbulent dynamics of fluids shape our ocean currents and atmospheric patterns, yet predictable cycles. Like the seasons or the trade winds, emerge from this very turbulence. Volcanoes, earthquakes, and the slow, powerful process of mountain formation are all products of chaotic forces acting over immense timescales, sculpting landscapes with remarkable order and regularity. Even our planet's ecosystems operate on this principle. It's the complex web of species interactions, predator-prey dynamics, and nutrient cycles create stable patterns of biodiversity, all happening amidst the unpredictability of environmental change. In this dance, chaos and order coexist, producing resilience, adaptability, and ever-increasing complexity. These principles of chaos and order don't stop with nature. They extend deep into human society and technology. Our bustling cities, our global economies, and our vast communication networks emerge from the countless interactions of individual decisions. It seems chaotic at the level of a single person, yet coherent, predictable patterns form at the macro scale. The flow of traffic, the structure of social networks, and even the internet itself all show self-organizing behaviors that are surprisingly similar to cosmic filaments and clusters. Science and technology are built on this very understanding of finding order within chaos. Chaos theory is a vital tool in climate modeling, electrical engineering, and even the development of artificial intelligence. By recognizing patterns in systems that seem random, we humans can predict, adapt, and innovate, echoing the very processes that shape the universe itself. Humans seem to have an innate drive to find patterns and impose order on our surroundings. It's possible that our very cognition reflects the universe's own tendency toward creating structure. The neural networks in our brains, firing in complex but coherent patterns, look remarkably like the large-scale networks of galaxies and clusters. So, in a way, when we observe the cosmos, we are witnessing a reflection of the same principles that organize our own minds. Then yet, this balance between chaos and order is incredibly delicate. Natural disasters, sudden climate shifts, and cosmic events are constant reminders that order is never absolute. The same immense forces that create galaxies can also destroy them. Our civilization depends on maintaining a fragile balance between chaotic elements and our organized systems. Understanding the cosmic principles that gave rise to order can teach us how to better manage the immense complexity we face here on Earth. By tracing this incredible journey, from quantum fluctuations to galaxies, stars, planets, and life, we see a profound truth. Chaos is not the enemy of order. It is the raw material for it. Every pattern we observe in the cosmos, every system we build on Earth, and every structure within our own bodies is a testament to the universe's remarkable ability to transform randomness into organization. As we look out to the stars, we are also looking inward. The order we perceive in the vastness of space mirrors the order that arises in our own lives, in our societies, and in the very structures of life itself. Chaos, when harnessed by laws, gravity, and natural processes, is not destructive, is generative. From the very beginning, humans have looked up at the night sky and wondered. We've always been on a journey to understand the universe, a quest that has taken us from simply gazing at the stars to building the most powerful telescopes and supercomputers imaginable. The story of how we uncovered cosmic order is just as incredible as the universe itself. Long before we even had a name for it, ancient civilizations were trying to find patterns in the sky. They noticed the predictable paths of planets, the regular phases of the moon, and the familiar arrangements of stars that returned each year. The Babylonians charted the stars, the Maya built observatories, and the ancient Greeks imagined the heavens as perfect celestial spheres. These early observations were the first hints of an underlying order in what seemed like celestial chaos. They didn't know about quantum fluctuations or cosmic filaments, but they recognized that the heavens weren't random. They were governed by rules. This was the first crucial step. Then came the scientific revolution, which completely changed our view of the cosmos. Copernicus courageously declared that the Earth was not the center of everything. Galileo, with his newly invented telescope, saw moons orbiting Jupiter, proving not everything revolved around us. And Isaac Newton, with his laws of gravity, gave us a mathematical language to describe this cosmic dance. For the first time, order was something we could measure and predict. The movements of planets and stars could be calculated with stunning accuracy. But even with these breakthroughs, the true large-scale structure of the universe was still a mystery. The stars we could see were just a tiny part of a much grander story. The 20th century finally gave us the tools to see the universe's grand architecture. In the 1920s, Edwin Hubble made a groundbreaking discovery. He observed that distant galaxies weren't just sitting there. They're all moving away from us. This revealed that the universe is expanding and pointed to a single origin point, the Big Bang. Later, massive projects like the Sloan Digital Sky Survey began mapping the positions of millions of galaxies. And when they put all that data together, an incredible picture emerged. Galaxies weren't scattered randomly like dust. They formed a vast, interconnected network of filaments, clusters, and giant empty voids, the cosmic web. Theory and observation had finally met, perhaps the most profound discovery linking the universe. As chaotic beginnings, to its present order, was the cosmic microwave background, or CMB. Accidentally detected in 1965, the CMB is the afterglow of the Big Bang, a faint radiation filling all of space. When we mapped it with incredible precision using satellites, we saw tiny, almost imperceptible temperature variations, differences of just 1 part in 100,000. These tiny fluctuations were the echoes of quantum randomness in the infant universe. They were the seeds from which all structure grew. Billions of years later, these minuscule ripples would evolve into the galaxies, clusters, and filaments we see today. It was the ultimate proof that the largest structures in the universe grew from chaos at the smallest possible scales. Observing the universe was one thing, but understanding how it evolved was another challenge entirely. This is where supercomputers came in. Starting in the late 20th century, astrophysicists began creating virtual universes, simulating the interactions of billions of particles under the influence of gravity, dark matter, and cosmic expansion. Groundbreaking projects like the Millennium Simulation showed something astonishing. When they ran these simulations with the simple laws of physics and random initial conditions, the same complex structures we see in the real universe, the filaments, clusters, and voids of the cosmic web, merged naturally. This demonstrated that the universe's order isn't an accident. It's an inevitable consequence of its fundamental physical laws. Our quest for understanding isn't just limited to looking up at the sky. We're also looking down at the smallest scales imaginable. Particle accelerators like the Large Hadron Collider smash particles together at incredible speeds, recreating the conditions of the early universe and confirming the physics that governed its birth. Experiments in quantum mechanics and chaos theory are helping us understand the fundamental processes by which order can spontaneously arise from randomness. It's a two-pronged attack, looking at the biggest structures in the cosmos and the smallest particles in the lab to piece together the full story. This incredible journey of discovery was driven by brilliant minds. Edwin Hubble showed us the universe was expanding. Arno Penzias and Robert Wilson found the echo of the Big Bang. Alan Guth's theory of cosmic inflation explained how tiny quantum jitters were blown up to cosmic size. Vera Rubin's work on galaxy rotation gave us the first strong evidence for dark matter, the invisible scaffolding that holds everything together. And scientists like Simon White and Volker Springel pioneered the computer simulations that brought the evolution of the cosmic web to life. Each of them added a crucial piece to the puzzle. So, this journey from ancient stargazing to advanced supercomputer simulations reveals a fundamental truth. Human curiosity has the power to trace the path from chaos to order by observing patterns, testing theories, and building virtual universes. We've learned not just what the universe looks like, but how it organizes itself. We are, in essence. Learning to read the cosmic blueprint first sketched by quantum fluctuations, then amplified by inflation, and finally built out by gravity and dark matter. We are witnessing an amazing convergence of observation, theory, and computation, revealing a universe that is, at the same time, both chaotic and exquisitely ordered. But even with all these incredible achievements, our story is far from over. We now know enough to be in awe of the universe's intricate design, but the biggest questions still linger. Will this cosmic order last forever? Could dark energy eventually tear it all apart, returning the universe to a state of chaos? And what is this principle of structured chaos, of order emerging from randomness? Tell us about our own future, both here on Earth and out there in the cosmos. Have you ever looked up at the night sky and wondered how all of this came to be? From the tiniest spark to the grand cosmic tapestry we see today, the universe is a story of chaos and order, a dance that has been unfolding for billions of years. The galaxies, the clusters, and the intricate web connecting them are all just snapshots in time. It all started with the wild random chaos of quantum fluctuations. Yet somehow, out of that randomness, incredible order emerged. But the story isn't over. Where is it all heading? Our universe is expanding, and not just expanding, it's accelerating. A mysterious force we call dark energy is pushing everything apart. The beautiful cosmic web that holds galaxies together is slowly being stretched thin. Fast forward tens of billions of years, and our bustling cosmic neighborhood could become a collection of lonely islands. Galaxy clusters will drift apart, separated by immense, ever-growing voids of nothingness. If this continues, gravity itself might lose its grip. The cosmic web could dissolve, leaving behind a universe in a state known as heat death. Imagine a perfectly uniformed, featureless expanse, where all energy is evenly spread out, and nothing interesting can ever happen again. A universe returned to a different kind of chaos, not of random energy, but of eternal, unchanging silence. But don't despair just yet. Order is resilient. It's a fighter. Even as the universe expands, pockets of creation will persist. In dense regions of gas and dust, stars will continue to be born, lighting up the darkness. Galaxies will collide and merge, creating new, larger structures. And at the heart of it all, black holes will continue to be cosmic sculptors, shaping everything around them with their immense gravity. So chaos doesn't just wipe the slate clean. It creates a dynamic tension, a constant push and pull that forces the universe to adapt and evolve. This brings up some mind-bending questions. Is order just a temporary phase, a fleeting moment of complexity in an otherwise chaotic existence? Or could the universe be caught in a grand cosmic rhythm, endlessly cycling between structure and dissolution? The story of order isn't just written in the stars. It's happening right here, right now. Life on Earth is the ultimate example of structure emerging from chaos. Think about it. From a primordial soup of simple molecules, incredibly complex life forms arose. So even if the universe is heading towards a cold, dark end, it doesn't mean the end of complexity. Pockets of order, perhaps in the form of technological civilizations, advanced artificial intelligence, or even forms of organized information we can't yet imagine, could carry the torch. Some thinkers even speculate that life and intelligence are the universe's ultimate defense against entropy, a way to create and preserve order locally, even as the cosmos as a whole trends toward disorder. In this incredible view, our very consciousness becomes a key player in the cosmic game of creation. This cosmic dance between chaos and order isn't just about physics. It's deeply philosophical. The universe shows us that randomness isn't the enemy of structure. It's the raw material. It's the blank canvas. From the quantum foam that sparked the Big Bang to the cosmic filaments that form the skeleton of the universe, chaos provides the potential for complexity to arise. Life, intelligence, our very thoughts, they are all extensions of this fundamental principle. We see the same patterns everywhere, in the branching of a galactic supercluster, the veins of a leaf, and the neural networks in our own brains. It's a profound realization. Our existence is not some fluke. We are a product of the universe's innate tendency to organize itself. We live in a cosmos where chaos is generative, where disorder gives rise to breathtaking complexity, and where order is a natural, beautiful consequence. And the best part is, we're just beginning to understand it all. With new tools like the James Webb Space Telescope, we're peering back to the dawn of time, watching the first structures emerge from the primordial fog. Next-generation observatories will let us listen to the echoes of cosmic collisions, revealing how gravity sculpted the universe. At the same time, supercomputers are running massive simulations, helping us uncover the universal rules that connect quantum randomness to the grand cosmic architecture and even the emergence of life itself. Perhaps one day, we will finally grasp the full story of how chaos so masterfully organizes matter, energy, and information across every conceivable scale. Even with all our progress, the biggest questions remain. Will the universe eventually fade into a uniform structureless void? Is order an unbreakable law of physics, or just a lucky break? Could life and intelligence survive as tiny islands of complexity in an ocean of entropy? And perhaps the most profound question of all, what does the universe's incredible ability to create order from chaos tell us about our own place in it all? The answers are still out there, waiting in the darkness between the stars. When we look up at the cosmos, we're seeing our own origin story. The story of the universe is the story of chaos and order woven together. It began with quantum randomness, was amplified by cosmic inflation, and then sculpted by gravity. Dark matter and dark energy took the lead, guiding the formation of filaments, clusters, and voids. And here on Earth, those same cosmic processes planted the seeds for planets, life, and consciousness. It seems that order isn't some miracle. It's the natural, inevitable outcome of chaos. The universe teaches us that complexity can arise from randomness, that beautiful patterns can emerge from nothing, and that even in the most turbulent conditions, structure, life, and intelligence can find a way to flourish. So, the next time you feel small under the vast night sky, remember this: you are not just an observer. You are an active participant in a universe where chaos gives birth to order, where randomness generates beauty, and where the fundamental laws of nature are writing the epic story of existence itself. You are a living, breathing, thinking piece of that story, a testament to the incredible power of structured chaos. Thank you so much for joining me on this cosmic journey. If you enjoyed this exploration of the universe's biggest secrets, don't forget to like, subscribe, and hit that notification bell so you don't miss our next adventure into the cosmos.